Chapter 3, Section 4, Exponential Growth or Decay. If something is either growing or decaying, it means the rate at which the amount of substance, whatever it is growing or decaying with respect to time is equal to some constant times the amount of the substance. And this differential equation will always have the solution A equals A sub 0 times E raised to the kt, where A sub 0 is the amount of substance present at time 0, or we call it the initial amount. A is the amount of substance present after time has passed, the time being the t that's in this exponent, which is also in the denominator of the differential equation. E is a constant. The constant k, will be a negative number when something is decaying, and the k will be a positive number if the substance is growing. So we use the same formula. So on page 360, exercise 2 says carbon-14 has a decay rate of 0.012097% per year. That means the rate at which the amount of carbon-14 is decaying, the rate at which it's decaying with respect to time, is equal to negative 0.00012097 times the amount of carbon-14 present. Notice the number in the given sentence said that the rate was 0.012097%. So in this differential equation, we have to move this decimal point 2 places to the left to get rid of the percent sign. And this is a negative number here because the carbon-14 decays. If it was growing, it would be if it was something growing, we would use a positive number in front of this n. Part A, let n sub 0 represent the amount of carbon-14 present at t equals 0. Find the exponential function that models the situation. Well, that's going to be exactly what's over here, except we're using the letter n instead of the letter a. And the k is the number that's given in the problem. So it's n, that means amount of carbon-14, equals n sub 0 times e to the kt. K is this number in front of n up here, negative 0.00012097. It's e to the kt. That's the answer to part A. Part B. Suppose 200 grams of carbon-14 is present at time t equals 0. The amount of carbon-14 at time 0 is given. Put that number here, 200 grams. How much will remain after 800 years? 800 years is time. So in place of t for time, we put 800 years. And n is what we're looking for in part B. That'll be the amount of carbon-14 after 800 years, if there's 200 grams at time 0. put all of this in the calculator. 200 times E raised to the negative 0.000120097 times 800. And this comes out to be, N will be approximately 182 grams of carbon-14 after 800 years. This shows that carbon-14 decays very slowly. 200 grams, it took 800 years for it to decay to 182 grams. Part C, after how many years will half of the 200 grams of carbon-14 remain? After how many years means find T. So initially there's 200 grams. Half of that would be 100. So we're going to replace this N with 100. The N sub 0 is 200. At times 0, that's how many grams there are. Next to that, we're going to put E to the negative 0.000120097 T. And the T is what we're trying to solve for. The time it takes for 200 grams to become half of that. So we divide both sides by 200. When we divide 100 by 200, we get 1/2, or 0.5. And the other side, the 200, the green and the yellow cancel. We still have E to the negative 0.000120097 T. Now we take the natural log of both sides. If two things are equal, the natural logs must be equal. Or you could say, if you could do something to one side of the equal sign, like take the natural log. We say if we do that, we have to do the same thing to the other side of the equal sign. And the reason we use logs is when we have the log of something with an exponent, we can drop the exponent out to the front of the log like this, negative 0.000120097 T. That's the exponent. That's going to be in front of the natural log of E. And now we're going to divide both sides by negative 0.000120097. We're dividing both sides by negative 0.000120097. So I will do this division on the calculator. The natural log of 1/2 divided by negative 0.000120097. And I'm rounding to the nearest whole number, 5,730. That's an approximation. This side of the equal sign over here will just be T, because this number cancels with this number, and the natural log of E is 1. So that's the time it takes for the 200 grams of carbon-14 to become 100 grams. 5,730 years. And therefore, we call this number the half-life of carbon-14. That's how long it takes any amount of carbon-14 to become half of that amount. scientists use this information a lot, archaeologists. So number 12 on page 361 says, how old is a piece of wood that has lost 90% of its carbon-14? So we'll start with this formula. N equals N sub 0 e to the kt. Suppose the initial amount of carbon-14 in the wood is 100 grams. I'm just making up this number. If the wood lost 90% of its carbon-14, that means it would have 10 grams left. So the amount of carbon-14 in this piece of wood initially, we're pretending it's 100 grams. After a certain amount of time, it has 10 grams left because it lost 90%. And the time it takes for the 100 grams to become 10 grams, we don't know that time. But this K, we actually know, because for carbon-14, it's always the number that we used in the last problem. So we can say 10 equals 100 e to the negative 0.000120097 t. And we're going to find the time it takes for 100 grams of carbon-14 to become 10 grams. Then we'll know how old the piece of wood is. So what we do now is divide both sides by 100. Ten divided by 100 could be written as 0.1 or 1/10. Either way you want to write it. The other side of the equal sign will be e raised to the negative 0.000120097 t, because these hundreds cancel. Now we're going to take the natural log of both sides. The natural log of the left side has to equal the natural log of the right side. The reason we use logs is when we have the log of something with an exponent, we can drop the exponent down in front of the log. So it's going to be this exponent times the natural log of e. No exponent anymore. Now we're going to divide both sides of this equation by negative 0.000120097. So we'll do this division on my calculator. The natural log of 1/10 divided by negative 0.000120097. And if I round to the nearest whole number, this division on the left side here, I get 19,034. The right side of the equal sign, this number cancels with this number. The t will get brought down, but the natural log of e is 1. So this says t times 1. And t is measured in years. So this piece of wood is about 19,034 years old. Very old piece of wood. Yeah, In chapter 3, section 5 is to just learn a couple more derivative formulas. We might have mentioned these already. One is the derivative with respect to x of any number, a number raised to the u, is itself times the natural log of that number times the derivative of the exponent with respect to x. I believe we've already talked about that. I'm going to say some more. And we also have mentioned this, the derivative of the natural log of something. By the way, this something here is usually in parentheses itself. The derivative of the natural log of u is 1 over u. That means 1 over whatever's inside these parentheses, times the derivative of u with respect to x. And here's a definition of logarithms that is not part of calculus. This is pre-calculus. When we write the log of something, and we have down here a subscript. Subscript is called the base. And this will equal something. Let's say, I don't know, j. Whenever we have an equation like this, it means the same thing as this base, which is down here in the basement. That's how I remember this. The base is down below, like in the basement. And this thing over here is the exponent. So I repeat the phrase over and over again, that a log is an exponent. There's the log. This symbol is the same as the word is. An exponent. A log is an exponent. That means the j is the exponent on the base, and that equals whatever's written in this spot. This is the definition of a logarithm, any logarithm. So in the past few examples, I've been saying the natural log of e is 1. When we write ln for logarithm, we mean the log with base e. And the base, which is ordinarily in the basement, is understood to be e anytime we write ln. So here's the base down below in the basement. This is the exponent, because a log is an exponent. A log is an exponent. So the 1 over here is the exponent. And this base raised to this exponent equals whatever's written right there. So the reason I keep saying the natural log of e is 1 is because this is true. So on page 368, exercise 6, g of x equals x to the 5th times 3.7 raised to the x. Directions are differentiate, which means find g prime of x. The derivative of a product is the first, which is red, times the derivative of the second, which is green, plus the second, which is green, times the derivative of the first. The derivative of a product is the first, which is x to the 5th, times the derivative of the second. The derivative of a number raised to the x is that exact same thing, that number raised to the x, times the natural log of that number, times the derivative of the exponent. The derivative of 1x is 1. So far I've written the first times the derivative of the second. We need plus the second, which is 3.7 raised to the x, times the derivative of the first. first is 1x to the fifth. The derivative of 1x to the fifth is 5x to the fourth. And all of this is the answer. You really can't do much to simplify this except to leave that 1 out. So I won't even bother simplifying it. When you write the answer, of course, you don't need this 1, but you need everything else. So notice the derivative of x to the fifth is 5x to the fourth. But when we have a number raised to an exponent, the derivative is these three parts. The derivative of 3.7 raised to the x is itself times the natural log of the base number times the derivative of the exponent. So number 8 on page 368 says y equals 4 raised to the x squared plus 5. 4 is a number raised to the x squared plus 5. So the derivative of y with respect to x, the rule applies for the derivative of a number raised to an exponent is itself times the natural log of the number 4 times the derivative of the exponent. And that's all there is to number 8. Number 18. G of x equals the log of 9x minus 2, base 32. And we're trying to differentiate this. Before we differentiate this, we're going to rewrite this as the base, which is easy to find because it's in the basement, raised to the exponent. I know that what's over here is the exponent because reading this sentence backwards, it would say to me a log is an exponent. Therefore, g of x is the exponent on the base. And this base raised to this exponent equals whatever's written right there. So now that I've rewritten this, I'm going to differentiate both sides. The derivative, the left side is a number raised to something. The derivative of 32 raised to the g of x is the same thing, 32 raised to the g of x, times the natural log of that number 32, times the derivative of this exponent, which would be written like this, g prime of x. The derivative of g of x is g prime of x. So I just differentiated the left side, so I have to differentiate the right side. The derivative of 9x minus 2 is 9. And now we're going to divide both sides of this equation by all the stuff next to g prime of x, because then we'll have g prime of x all by itself. So dividing the left side by 32 raised to the g of x times the natural log of 32. Because I'm dividing this side by all that, I have to do the same thing to the other side. 32 raised to the g of x times the natural log of 32. So left side of the equation, cancel, cancel, but we still have g prime of x. The right side is a 9. Then down here, instead of writing 32 raised to the g over x, I'm going to put this there. This and 32 raised to the g over x are the same thing. They're equal to each other. So where I see 32 raised to the g of x, I can put 9x minus 2 there. So right here, instead of writing that, we write 9x minus 2 in parentheses. And that natural log of 32 just gets brought down, and we're done. I'm going to do one more, and then this video will be done. Number 22. Y equals the log of x to the fourth minus x, and it's log base 9. because a log is an exponent, this must be the exponent on the base 9. I know 9 is the base because I see it down in the basement. Y is the exponent because a log is an exponent. 9 raised to the y equals whatever's written right there. Going from here to there is called the definition of logarithms. Now we're going to differentiate both sides. The derivative of the left side, the derivative of 9 raised to the y is 9 raised to the y times the natural log of 9 times the derivative of the exponent with respect to x. The derivative of the right side is 4x to the third minus 1. And now we divide both sides by all the stuff in front of dy dx. So dy dx equals everything over here, 4x to the third minus 1, divided by 9 to the y, 9 raised to the y, times the natural log of 9. We just divided both sides by 9 to the y times the natural log of 9. But that 9 raised to the y that we just wrote down here can be replaced with this. So that makes the final answer dy dx, derivative of y with respect to x, equals 4x to the third minus 1 over x to the fourth minus x in parentheses times the natural log of 9. Just replacing this with what it equals.